Good morning, class. Yeah, so our topic today is we are continuing from the last class, waves. Okay, so we in our last class, we talked about the classes of waves. We dealt with mechanical and what electromagnetic, right? And also we dealt with types of waves, transverse and what longitudinal. So last week we dealt with the transverse waves and progressive waves. So today we are dealing with longitudinal waves. Okay. Now, in our last class, I told you that transverse wave is classified in we have the crest and the trough, right? But in longitudinal wave, we have the compression and the rarefaction. Okay. So the compression is where the pressure is more. The compression in longitudinal wave is where the pressure is more, while in the rarefaction, it's where the pressure is less. Okay. Now, um, longitudinal wave, we have types of longitudinal wave. We have the sound wave. Okay, the sound wave is a type of longitudinal wave. So today we are dealing with okay, stationary wave too is type of longitudinal wave. So today we are dealing with stationary wave and stationary waves in sound and also stationary waves in strings. Okay, stationary waves in sounds and stationary waves in strings. Okay, so we'll deal with first of all we'll define what stationary wave is. Stationary wave is a wave that is formed. Okay, stationary wave is a type of wave that is formed from two progressive waves. Stationary wave is a wave that is formed from two progressive waves with the same amplitude, frequency, the same amplitude, frequency, and speed. Okay, stationary waves are waves that are formed from two progressive waves with the same amplitude, frequency, and speed. Now, are these two progressive waves are superposed, or we call it superpose, or superimpose with one another. So is this superimposition that causes the stationary wave? These superimpositions of the two progressive waves that causes the what? The stationary waves. Now, for stationary waves, this is the diagram for stationary wave. Now, first of all, I want to explain something. In a stationary wave, there is what we call the incident wave, and the what? Reflected ray, the reflected wave, the incident ray and the reflected ray. Okay? Now, the incident ray is the original wave. The incident wave is the original wave that was given off. Why the reflected wave is the wave that was what? Returned back. Now, how is this wave returned back? Now, assuming a vibrator, assuming a vibrator sends a wave. Now, in stationary wave, it's always fixed. Stationary waves are always what? They are always fixed. Now, this is the obstacle. Now, once this vibrator sends a wave to this obstacle returns back the wave. Don't mind my drawing. Now, this is just what stationary wave is. This obstacle returns back the wave. Example: if you know people that use skipping rope, skipping rope. Okay, if you hold one part of the skipping rope and another person holds the other part of the skipping rope, by the time you are shaking it vigorously, the person holding the left part of it and the person holding the right part of it, they are moving the rope at the same speed. Okay, at the same speed. Now, that speed, that wave that is formed is what we call what? The stationary wave. Because one part of the wave is what? Fixed. And the other part also is what? Fixed. So when you are looking at that wave, it will be as if this place, this part of it, these sides are moving. Okay? It will be as if they are, no, they're actually moving, but in terms of physics, they are what? They are fixed. The wave profile is what? Is stationary. It does not move. But you are moving it as humans, you are moving the rope. But in physics, the wave profile is what? Stationary, because they are in one point. So this is what defines what? Stationary wave. Now let's write. When a wave travels a given path, when a wave travels a given path, when a wave travels a given path and strikes an obstacle, when a wave travels a given path and strikes an obstacle, this is the obstacle. This is the incident ray. Incident ray. This is the reflected ray. Reflected ray. Reflected ray. This obstacle is what we call the reflector, either the reflector or the obstacle. Either which one you want to call it. The reflector, let me make it bold. Obstacle. So when a wave travels a given path and strikes an obstacle such that it is reflected perpendicularly, such that it is reflected perpendicularly, such that it is reflected perpendicularly and returns along the same path, we call that wave a stationary wave. When a wave travels a given path and strikes an obstacle, such that the wave is reflected back perpendicularly, such that the wave is reflected back perpendicularly along the same path, we call that wave a stationary what? A stationary wave. We call it a stationary wave. Now, the incident ray, the incident the incident wave and the reflected wave, the incident wave and the reflected wave superimpose. The incident wave and the reflected wave superimpose to form a stationary wave. The incident wave and the reflected wave, the incident wave and the reflected wave superimpose. This is the incident. It strikes the obstacle, it returns back. So this wave profile is what is a superimposition wave profile. Okay? Now the incident wave and the reflected wave superimpose to form a stationary wave. To form a stationary wave. In which the wave pattern in which the wave pattern stays put, in which the wave pattern stays put, even though the waves themselves are still moving, even though the wave themselves are still moving. Even though the wave themselves are still moving. Example is the rope example I gave you, okay, that is described for you. The wave pattern, as you are moving the rope, the same the other person too is the same speed, the same amplitude, okay. The wave, even though the rope is still moving, the wave pattern is what? Fixed. As long as the speed, as long as the both persons holding the fixed end are fixed, they have the same speed, they have the same amplitude, and the same what? Frequency. Okay. Now, for you to have a stationary wave, listen, for you to have a stationary wave, okay, for you to have a stationary wave, the frequency, the amplitude, the frequency, the amplitude, and the speed must be the same. For a stationary wave to happen, the frequency, the amplitude, and the speed must be what? The same. If they are not the same, a stationary wave cannot happen. If they are not the same, a stationary wave cannot happen. Now, once a stationary wave, so once a stationary wave is formed, now they are in this wave, there is what we call this lowest part, the part of no displacement. This part, there's a straight line here. The part of no displacement, the part of no displacement, this part is what we call the what? Node. This is the node. This part where the amplitude, this part are what we call the what? Node. But this part where there is maximum displacement, this part where there is what? A maximum displacement is what we call the what? Antinodes. So in a stationary wave, we have the what? Nodes, and we have the what? Antinodes. The nodes and the antinodes. Okay, let's continue. The incident and reflected wave. The incident and reflected wave. The incident and reflected waves form what we call the nodes. Form what we call the nodes. Form what we call the nodes and the what? Antinodes. Form what we call the nodes and the antinodes. Now the node is where the wave, the node is where the wave meets at rest. The node is where the wave, both the reflected and the incident wave, the node is where both the reflected and the incident wave meet at what? At rest. Okay? The node is where the reflected wave and the incident wave meet at what? Rest. You open bracket and put antiphase. 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 And the antinode is where the waves meet in phase. The antinode is where the waves meet in what? In phase. The antinode is where the waves meet in phase. So this node is for okay. Now for the For the nodes, the amplitude is equals to 0. For the antinodes, the amplitude is at a maximum displacement. The amplitude can be 2, it can be 3, it can be whatever. But for the nodes, the amplitude is equals to what? 0. Now, the distance between two successive nodes, the distance between two successive nodes. Hello, listen. Listen. The distance between this place and this place, two successive nodes. This place and this place. The distance between two successive nodes is half the wavelength. The distance between these nodes and this node is half the wavelength. The distance between two successive nodes is half the wavelength. Now, let's assume you have this wave. Hello, listen. You have this, and you have this, and you have this. At this point, you have one node. This place are nodes, and this place is the what? Antinode. This is node. This is node. Yeah. Then this is antinode. This is what? Antinode, right? This is node. This is node. This is what? Nodes, right? This is antinode, and this is what? Antinode. Okay. Now, for this place, for this wave, the n is equals to 1. The n, one cycle, n is equals to 1. 2 cycles, n is equals to what? 2. 3 cycles, n is equals to what? 1 cycle. This is 1, this is 2, this is 3. So for each of this wave, the length is fixed. For each of this wave, the length is fixed. Now, I said the length is equals to the length of this wave, the length of each of this wave. The formula is lambda n over what? 2. Lambda n over 2. That's the length of each of this wave. This is the formula to find the length. Okay, where n is equals to 1, or n is equals to 2, or n is equals to what? 3. Now, if you want to find the wavelength lambda, will become what? If you want to find the lambda of this, what will you have? 2L over what? 2L over n. Thank you.
So you told me like.
Well, yeah.
Yes.
This is just n now. N lambda n. This n here, this n is dependent on the number of loops you have. Okay, this n here, the wavelength of n1 is this. The wavelength of n2, you put wavelength 2. The wavelength of n3, you put what? Wavelength what? 3. Now, for instance, to find the wavelength of this one, your n is equals to 1, abi? So wavelength 1 is equals to what? 2L over what? N is equals to 1, abi? So you have wavelength is equals to what? 2L. Wavelength is equals to 2L. For wavelength 2, 2L over what? 2. Wavelength is equals to what? So wavelength 3L over what? 2L, thank you. 2L over what? 3. So your wavelength will be what? 2L over 3, right? But if you want to do this one, then your length for this one will be what? 3 over 2 wavelength, right? If you cross multiply, it's going to be 3 times wavelength is what? 3 wavelengths, right? Then 2, you divide. Then this one will be what? L is equals to what? Wavelength. The same thing. This one will be what? L is equals to what? Wavelength over what? 2. This L. Wavelength over 2. Wavelength over 2. For this one, L is equal to what? Wavelength. Then for this one, L is equals to what? 3 over 2 wavelength. Let's continue. Standing waves. Yes? Which one?
This one that you did.
This one?
Yes.
Everything?
Yes, sir.
Okay. Now, this wave is what we call a loop. Okay? This one is loop 1.
You can't see the ball from here.
You cannot see the ball.
Yes. Like this side.
Okay. You can see it now.
Yes, sir.
Okay, this side is a loop. This one cycle is one loop. This 2 cycle is 2 loops. These 3 cycles, this is cycle 1. From here is cycle 1. Then it goes here, cycle 2. It comes back here, cycle 3. Now, the distance between 2 nodes is given as what? L. Okay? And L for this one, for these 2 nodes is what? Wavelength over what? 2. The distance between this one and this one, distance between this place and this place is given as what? Lambda over what? Lambda equals to what? Wavelength. How did you get lambda equals to wavelength? Now, the formula for finding length is equals to what? N lambda n over what? 2. Now, this n here is dependent on this n here. So if you are saying n, if you are solving for this question, n will be what? 1. If you are solving for this one, n will be what? 2. If you are doing for this one, n will be what? 3. Good. So for here, your length will be what? Put n as 1. And here you have lambda 1 divided by 2. So your n here will be what? Lambda over what? 2. That's why I got lambda over 2 here. Do you understand now? Now for this one, n is equals to what? 2. So your L will be what? 2 lambda 2 over what? 2. 2 cancel 2. L will be what? Lambda what? That's why I got L equals to what? Lambda. Do you understand? Now for this one, n is equals to what? 3. L is equals to 3 over 2 lambda 3. So your L here will be what? 3 over what? 2 lambda 3. That's how I got L is equals to 3 over 2 what? Lambda here. Now, if you want to find your wavelength, for your wavelength for this one, where is it? Wavelength for this one, okay? Since L is equals to wavelength over 2, wavelength is equals to what? 2L for this one. Now, since L is equals to wavelength for this part, your wavelength will be what? L for this one. Now, for this part, since L is equals to 3 over 2 wavelength 3, L is equals to 3 over 2 wavelength 3, your wavelength will be what? wavelength will be equals to what? 2L over what? 3. This is your wavelength for this part. This is your wavelength for this part. This is your wavelength for this other part. Now, continue. Let's continue. Standing waves. Standing waves contain multiple frequencies. Standing waves contain multiple frequencies. Where's the poster? Poster. Oh, sorry. Standing waves contain multiple frequencies. Standing waves contain multiple frequencies. The fundamental frequency F naught, the fundamental frequency F naught, the fundamental frequency F naught is known as the fundamental frequency F naught is known as the first harmonic. F0. F0 is the first harmonic. First harmonic. The other frequencies F. Now this one, sometimes people put F1, sometimes people put F0. So it's either F1 or F0. So the other frequencies F2 is equals to, the other frequencies are a multiple of the fundamental frequency. Multiple of the fundamental frequency. That means the other frequency F2 be what? 2 times F0. F3 is equals to 3 times F0. F4 is equals to 4 times F0, and so on and so forth. Multiples of the fundamental frequency F0 or F1, they are still the same thing. So now from F0, from F2, according to this thing, from F2 to F4, from F2 to F4, we call them what? Overtones. From F2 to F4, we call them what? Overtones. F1 is called what? First harmonic. From F2 to F4, we call them what? Overtones. Now, if you were given, now to find F0 is equal to V over 2L. F0 is equals to V over 2L. How did they get V over 2L? We know that V is equals to what? F lambda, right? V is equals F lambda. Now, for our first one, for this first one, lambda is equals to what? If V equals F over F, V equals F lambda. Now, F will be what? V over lambda, right? And sorry. Now, your L is equals to what? 2 what? Lambda. 2 what? Lambda. So this place, instead of putting lambda here, you put what? 2L. Why is that? Because if you now lambda is equal to what? For here, L over 2. Okay.
That is lambda over again.
2 over L.
Is equal to 2v over L. So this, the formula is supposed to be F equals to V over 2L.
Sir, L is equal to lambda over 2, not
Yes,
lambda.
not lambda.
No, in the diagram.
That like
Which one? This one?
Yes, it's lambda over 2.
Okay. For that first one,
Yes.
I gave you lambda over 2. Yeah, thank you. Lambda over what? 2. Thank you very much. So this place is lambda. This place is lambda. V equals to F equals to V over what? Lambda, right?
Yes.
So V will be what? From that one will be what? L over 2, right?
No,
2L.
2L.
Lambda will be equal to
Lambda will
Okay, yes, cross multiply. Thank you. So this one is sorry. L is equals to lambda over 2. Thank you. So multiply both sides, cross both sides. You have what? 2L. So that's why F naught is equals to V over what? 2L. That's the first harmonic, this first one. Now, overtones are pitches. Overtones, F2 to F4. Overtones are pitches. Overtones are pitches that are higher than the pitches that are higher than pitches higher than F naught. Pitches higher than F naught. Overtones are pitches higher than F naught. Example, if you, for most of you that used to sing, for most of you that used to sing, by the time they tell you sing do re mi fa so, by the time you are going from do and end with what? Do re mi fa so la ti do. From do to do, you are increasing the frequency of your voice, right? So from your first do is what? F naught. Your first do is F naught. Then do re, your re is what? F2. So the more you go, you end with your the last do, I think F7 or so. So by the time you finish all these things, you are going from your lowest pitch, your lowest frequency to what? The highest what? Frequency. So from F2 to F7 is what we call what? Overtones. In stationary waves, what's that? In stationary waves, the frequency in stationary waves, as the frequency increases, in stationary waves, as the frequency increases, the wavelength decreases. The stationary wave, as the frequency increases, the wavelength decreases. Can I clean this one? In frequency, in stationary wave, as the frequency increases, the wavelength will what? Decrease. And why is that so? Now, you know, for longitudinal wave, I gave you a diagram like this. The last time. Right? Now, in terms of this is another diagram of longitudinal. It's just like this. Okay. Now, this is the same thing as this one. This is what we call the compression. This is the compression. This part is what we call the what? The refraction. The compression and the refraction. Now, at this side, this is where you will need chemistry knowledge. At this side, you know air. You know air. For sound, now I want to use sound wave to explain this. Now, if you are asked to compress something, what do? You apply pressure, Abi?
Yes.
Good. Now, at this place, the pressure is higher. At this place, the pressure is low. At this place, the pressure is low. Okay? Now, at this side, the molecules, I'm using chemistry sense now. Now, at this part, the molecules is jam-packed together. The molecules are jam-packed together. That's why it's compression, I mean. And at this side, the molecules are what? Okay, for this side, the molecules are they are free. They are separated. They are free. Free molecules. For this place is jam-packed molecules. Okay. Now, for the compression for this part, the density of this is what? High. The compression has a high density. Compression has high density. Refraction has low density. Compression has high density. Refraction has what? Low density. Now, for this place, the compression has high frequency. The refraction has what? Low frequency. Now, I said in stationary waves, as the frequency increases, the wavelength what? Decreases. Now, if you are making noise, you know, your voice will be high. It means your pitch is high, your frequency is high. Now, I don't need to stay. If I stay far, I will hear you. If I stay very close, I will also hear you. Abi? So once the frequency is high, the distance between myself, the observer, and the person making the sound, the distance between myself and the person making the sound will be very what? Small. For compression, for stationary wave, by the time you are making sound, the distance between myself, the observer, and the person making the sound will be very low. For the refraction, the frequency is very low. The frequency is very low. The wavelength will be what? Very what? High. The frequency will be very low. The wavelength will be very high. Now, example, if you are ringing bell now, if you are ringing a bell, by the time you are ringing it vigorously, the frequency is high, right? If you are ringing the bell vigorously, the pitch, you'll be hearing the sound very well. Now, by the time I'm ringing it slowly, if I'm ringing the bell vigorously, just imagine yourself now ringing it. This is how the distance will be, because you are shaking it. So the distance is what? Very what? Small. Now, by the time you are ringing it slowly, back down, the distance will be what? High. So that's what explains this. The higher the frequency, the lower the what? Wavelength. The lower the frequency, the higher the what? Wavelength. So that's what explains that stationary wave. In stationary wave, the wavelength is low and the frequency increases while the wavelength what? Decreases. Okay, continue. At the antinode, any question? Any question? Stand up and ask your question. Now, okay. At the antinode, I'll soon stop, don't worry. At the antinode, 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 antinode. Node, 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 antinode, antinode, antinode. At the antinode, constructive interference, constructive interference, constructive interference occurs. At the antinode, constructive interference occurs. And why does this constructive interference occur? It's because at this point there is what? Maximum displacement. Constructive interference occurs because at the antinode the displacement is what? Maximum. For the node, destructive interference occurs. Destructive, yes. For the antinode, displacement is what? Maximum. For the node, destructive interference occurs. For the node, destructive interference occurs because at this point the displacement is what? Zero. The displacement is what? Zero. Okay, now let's do two questions, and I'm done. Question number one. JAMB 2011. The fundamental frequency of a standing wave. Question number one. The fundamental frequency of a standing wave. Is 50 Hz. The fundamental frequency of a standing wave is 50 Hz. 50 Hz. 50 Hz. The fundamental frequency of a standing wave is 50 Hz. Full stop. Calculate the first four harmonics. First four harmonics. Question 2. 50 Hz. Calculate the first four harmonics. First four. Yes. Question 2. The lowest note emitted by a stretched string. The lowest note. You know, if you stretch a string now, if you stretch a string and you leave it, what will happen? It will come back together, and when it's come back together, it's making what? A sound, right? Good. Now, the lowest note emitted by a stretched string has a frequency of 40 Hz. Has a frequency of 40 Hz. Full stop. The lowest note emitted by a stretched string. Has a frequency of 40 Hz. Full stop. How many overtones are there? Between 40 Hz and 150? 180, sorry. How many overtones or harmonics? How many overtones are there between 40 hertz and 180? Between 40 and 180. So you can do number one for me now. Number one is not hard. 3 overtones, Abi?
Yes, sir.
Good. Okay, for those that don't understand number one they said what? Calculate the first four. And I gave you F naught. F naught, fundamental frequency, is what? They now said calculate the first four. So they said you find F2, F3, F4, F5. Good. Now, and I said to find Fn, to find the second one, Fn is equal to what? N times what? F naught. F1 is equal to 1, sorry, F2 is equal to 2 times what? F naught. So we are looking for F2. F1 is the same thing as what? F naught. Do you understand? Now to find F2 is going to be what? 2 times what? 50. 3 times what? 4 times what? 5 times what? This one will give you what? 100. This one 150. This one. This one. That's for number one. Then for number that's all. That's all. Then for number two, the lowest note emitted by a stress string has a frequency of 40 hertz. How many overtones are there between 40 hertz and 180? How many overtones? Now, 40 hertz is F naught, right?
Yes.
They now ask you how many overtones are there between 40 and 180. So you start from F2. F2 will be equal to what? 2 times 40, right? F3 will be equal to what? 2 times what? 3 times 40. F4 will be what? 4 times 40. Now, 2 times 40 is what? 120, 160. So they now ask you, now if you do F5, 5 times 40, now you have crossed the 180 already. So you cancel it out. Do you understand? They said between 40 and what? 180. But F5 has crossed what? 180. So how many overtones do you now have? 1, 2, 3. So that's your answer. That's your answer. So yes. At this point, yes. Now there's no enter 180. They said between, in the middle. Okay. So after this hour in the afternoon, I'll come back in the afternoon. So in the afternoon we'll start with sound wave. We start with sound wave proper. At this point, we'll be talking about timbre, quality of sound. You've heard of timbre now. Quality of sound, beats, interference of sound, reverberation, and the rest. Echo. So thank you very much. Any question? Yes, what's your question? Yes?
This first question now.
This one?
Yes.
Okay.
I'm trying to it, but if you are sitting in a question, they have to give us one answer. I'm going to add it together to get the answer.
Add everything?
Yes.
No, don't add.
So,
Let's get the questions.
like,
Each of them are different.
Let's
No.
calculate the first four.
First four means just get the first four.
So we'll see it like this.
You will see it like this. Just get the first four. the first four. The first four frequencies. This one, and 1, 2, 3, 4. That's all. So you see your question because each of these frequencies are different. They are different. This one is 100, this one is 150, this